Good morning. This is Dr.S.B.MOHAN from EC Department, S.A.ENGG Engineering College. I welcome you all for this GATE coaching for the subject Network Analysis or Circuit Analysis. Today we are going to discuss about the topic on sinusoidal steady state analysis. When we consider the different supplies which are available, we got AC as well as DC, and it is proved that AC voltage or AC transmission will be comfortable for our utilization. When we talk about the generation side, again it has been proved that AC voltage will be more comfortable than DC, and of course the production cost also will be minimum along with that of DC, along with that of the transmission Right. So when we talk about the sinusoidal steady state analysis, we are going to deal with the parameters of the circuits which relates voltage, current, and of course power. Along with that of power, we got an additional term called as power factor. So when we consider this voltage, which will be represented as V of t, which is nothing but an instantaneous voltage so called, because the voltage signal is time dependent here, which is represented by Vm sin theta, where theta is nothing but omega t. Omega is equal to 2 pi f, which is nothing but the angular frequency. Now when we talk about this sinusoidal waveform, sinusoidal voltage, it is a time dependent voltage, and of course when we consider a conductor which is connected to this voltage, you will be getting a current flow, and that current flow will be also an alternating quantity. So therefore here this current also will be represented in terms of say an instantaneous value called as I of t, which is equal to Im sin theta, where theta is again omega t. Now when we talk about this interrelationship between the voltage and current, you got a factor called as phase angle. What is this phase angle? It is nothing but how far, or can say how the voltage and current will be interrelated to each other based upon this phase angle value. Right. Now this phase angle purely depends upon the components which are involved or which are connected in the circuit. When we talk about this network analysis or circuit analysis, we will be dealing with passive circuits or of course passive elements will be available in this, and we will be discussing about the relation between voltage, current, power for these components. What are passive elements? The passive elements are resistance, inductance and capacitance, and since when we talk about the steady state analysis, we will be having only inductance, resistance and capacitance. Now when you connect a pure resistance, what would be the relation between voltage and current, what would be the power value, and what would be a new term called as power factor, which is not available in the case of DC. Likewise, we'll be discussing for inductance as well as capacitance. Now we know that by Ohm's law, it is well known that at constant temperature, the current flowing through the conductor is directly proportional to the voltage applied. So here the proportionality constant will be the resistance, and of course we can state that V is equal to I into Z, I into R I mean. So this R is nothing but the resistance value which is offered by the conductor for the flow of current flow. Now if the temperature is varying, the resistance will also be varying. So therefore the Ohm's law, it is proved that it is only true for constant temperature. This is for DC circuit, since we are dealing with resistance alone. Since it has been dealt with resistance alone, we can say. Now when we talk about AC, here it will not be resistance alone, you will be calling it as impedance. What is impedance? Impedance is nothing but the resultant value of resistance and a term called as reactance. Where comes reactance here? When we consider an AC circuit, the AC circuit may have resistance, inductance and capacitance, and of course the inductance and capacitance will be depending upon frequency, and of course here AC signals deals with frequency, so we can state that the inductance and capacitance will be inferred as reactance, and of course these inference are imaginary values. So therefore when we talk about impedance, impedance will be the resultant value of resistance, which is nothing but the true value and of course real value. Here and of course the reactance is nothing but the imaginary value. So therefore the impedance is the resultant value of resistance and reactance. That is what we need to conclude here. Now when we talk about the voltage, this is the simple representation of an voltage wave for an for AC. Okay, so here this is your minimum value, this is your maximum value. Now when we talk about the current flowing at this place and the current flowing at this place, subsequently for the different locations of voltage or for different instance of voltage, the current flow may change. The current flow may change, and of course this change depends upon the components which we are connecting. The components which we are connecting. So now when we talk about a resistance, pure resistive circuit, which means that you don't have inductance or capacitance, then we can state that the voltage and current will be in phase with each other, which means that there won't be any difference in phase angle. Okay, what do you mean by phase angle? Here, if the voltage is minimum, the current flow also will be minimum. When the voltage reaches maximum, the current flow also will be reaching its maximum. See to that the magnitude may not be equal to that of voltage. The current flow will be having a lesser magnitude than voltage. Okay, when it goes to again negative maximum, the current flow also will be going to negative maximum, which means that the voltage and current are in line with each other. That is said to be called as in phase. So therefore, the phase angle between voltage and current will be equal to 0 for the case of pure resistive circuit. Now when we consider a pure inductive circuit, okay, it is not the case. What is inductance? Inductance, of course, it do consumes or it will store some magnetic charges. So when current flow is there, obviously it is well known that magnetic charges will be there. So the inductance will accumulate those magnetic charges, and of course it gets some time period for this accumulation, then it allows the current to flow in the remaining part of the circuit. Therefore, we can state that the current lags by some angle to that of the applied voltage. So here we can say the current lags the voltage and the angle will be 90 degrees for a pure inductive circuit. So we can state that the current flow lags voltage by 90 degrees. Current flow lags by 90 degrees to that of the voltage. Now, when we talk about capacitance, the capacitance will be having 90 degrees leading angle. Okay, the reason for it is the voltage takes some time to charge. Okay, the capacitance. So therefore, we'll be having an electric charge which is held in the capacitance, after which the voltage will be passed over. So therefore, we can state that the current leads your voltage by an angle of 90 degrees. The current leads the voltage by an angle of 90 degrees. Okay, so in the case of capacitance, current leads, and in the case of inductance, current lags. Okay, so this is what we need to conclude about pure resistance, pure inductance, and pure capacitance circuit. Okay, so before going to this previous slide, let us go for this inductance. So here when we talk about the pure inductance value, pure inductance circuit, I mean here the current flow is equal to Im sin omega t minus phi. Okay, so this minus phi indicates that there is a lagging angle of phi. Okay, this negative minus phi indicates there is a lagging angle of phi to that of this pure inductive circuit. And of course, for pure capacitive circuit, this plus phi, I is equal to Im sin omega t plus phi. This plus phi indicates that the current flow leads the voltage by an angle of phi. So for pure inductance circuit, the value of phi will be equal to 90 degrees in both the cases. Okay, so this is what these two equations conclude. Now, when we talk about the phasor representation, generally we will be representing, we'll be taking either of the parameters as reference. So here I have taken the current flow as reference, and here I have indicated voltage in terms of E. Okay, some authors they do refer voltage in terms of V or in terms of E also. So therefore here I have taken it as E. Okay, so therefore here the reference value is current, and of course this angle, lagging angle. Now this indicates that current leads the voltage by an angle of phi. So this plus phi indicates that the current is leading. The current is leading the voltage. Okay, or we can say the voltage is lagging by an angle of phi. Okay, so this is for capacitive circuit, pure capacitive circuit or impure capacitive circuit, whatever it is. Okay, and of course here the reference is current again. Here the voltage is leading, which shows that current is lagging by an angle of phi. So here this is for capacitance and this is for inductance. So when we talk about pure resistance, this E and the reference will be in line with each other. It will be in line with each other. That we have to confirm, right? So now when we talk about this AC components or AC parameters, okay, when we want to represent voltage, okay, you can represent in terms of instantaneous value. Of course, current also in terms of instantaneous value. So it is well known that product of voltage, instantaneous voltage and instantaneous current will be called as instantaneous power. Okay, so P of t is equal to V of t dot I of t. So that is your instantaneous power. Okay, so here when I want to represent a voltage in terms of AC parameter, okay, you have to represent in terms of RMS value. You have to represent in terms of RMS value, which is called as root mean square value. Root mean square value. So apart from root mean square value, you got another term called as average value. So average voltage, RMS voltage, average voltage as well as RMS voltage. So what is this RMS? What would be the value of VRMS or IRMS? VRMS will be equal to V max by root 2. Okay, Vm by root 2. Okay, if it is for current, it is IRMS is equal to Im by root 2. So we have seen the voltage equation. Okay, so V of t is equal to Vm sin theta. So we have to take this Vm. Okay, and we have to divide it by root 2. That gives us the RMS value. Okay, likewise for current, we have to take Im by root 2 to get your RMS values. Therefore, for any AC quantities, to calculate, okay, power, or if you want to calculate any parameters from terms of voltage or current, you have to consider the RMS value. Right. So apart from this RMS value, you got something called as average value, as I told you before. Okay, so average value is nothing but area under the curve by base, and RMS value is nothing but square root of area under the squared curve divided by base. Okay, so we got the average value and RMS value for different waves. So here we have dealt with sine wave, half wave rectified output and full wave rectified output. So when we talk about average value of sine wave and RMS value of sine wave, we got 2Im by pi. This is average value of sine wave, and RMS value of sine wave will be equal to Im by root 2. So we have to represent this. When we calculate 2 by pi, you will be getting 0.637. When we calculate 1 by root, you will be getting 0.707. Therefore, you have to remember this 0.637 into Im for calculation. Likewise, 0.707 Im for calculating the RMS value. Here I have taken the current as my parameter. If you want to take voltage, you can calculate voltage. If you want to calculate RMS value for voltage, we can take it as VRMS, which is equal to 0.707 Vm. Okay, likewise, when you want to calculate the value of average value and RMS value for half wave rectified output, you will be getting Im by pi as average value and 0.5 Im for RMS value. Okay, now when we consider, when we see these three equations, okay, these three values for your full, sinusoidal wave or half wave rectified or full wave rectified output. Okay, so here for pure sine wave and full wave rectified values, the average value, RMS value remains same. Okay, but for half wave rectified, the value is getting different. Apart from these things, you got two different factors which will be purely utilized for the AC quantity calculations. What are they? In the sense, it is form factor and peak factor. So form factor is defined as the ratio between RMS value and average value, and of course it is given by 1.11. It's a constant value. When you talk about peak factor is equal to peak value divided by average value. Okay, so therefore these two factors we have to keep in mind for calculating any parameters, right? In the case of AC quantity, that is what I have to conclude. Right now, as we discussed Impedance. Impedance is nothing but the resultant value of inductance and reactance, and the reactance is nothing but inductive reactance and capacitive reactance. So these two reactances, inductive reactance and capacitive reactance, are considered to be the imaginary part of your impedance value, and of course those two parameters are depending upon frequency. So here the inductive reactance is represented by XL and the capacitive reactance is represented by XC, which is given by omega L and 1 by omega C respectively. The units of these two reactance value will be ohms. Okay, don't get confused with the unit of inductance and capacitance. Inductance unit is Henry and capacitance unit is farad. Okay, but inductive reactance it is ohms, capacitive reactance is ohms again. Okay, so therefore we can have different combination of RLC. Okay, you may have pure resistance, pure inductance, pure capacitance circuit, or you may have RLC series circuit, RLC parallel circuit, RL series, RC series, or RL parallel, RC parallel, whatever. You may have any sort of combinations, and of course for all those combinations you have to consider these as the fundamentals for calculating the solution. Okay, so now here when we talk about the generalized summary of our RLC circuits or RLC parameter behaviors, okay, you can have these parameters as one column: characteristics and of course impedance in rectangular form, impedance in polar form. Why it is called as impedance in rectangular form and polar form? Because impedance is a complex number where you got real part and imaginary part, so you can represent a complex number in rectangular form as well as in polar form. Okay, so that is what. So for pure resistance, as we discussed, I mean voltage and current are in phase. For pure inductance it is current lags by 90 degrees, and for pure capacitance current leads by 90 degrees. For pure capacitance and inductance the angle is 90 degrees. Okay, likewise when we talk about the impedance, Z is equal to R plus J0 because it is a pure resistance circuit. For pure inductance Z is equal to JXL. For pure capacitance it is minus JXC. This plus and minus indicates that the angle, leading angle and lagging angle. So here the current lags by 90 degrees and here the current leads by 90 degrees. Okay, so this is what the phasor diagram representation of pure resistance, pure capacitance, and pure inductance and pure capacitance circuit, right? Okay. Now we have discussed something on pure inductance, pure capacitance, and pure resistive circuit. Apart from that, we require something called as power. So power, we got instantaneous power that I discussed before. It is given by V of t into I of t. But when we talk about the real time, okay, apart from this instantaneous power, you need to calculate something which is realistic. Okay, so based on that, you can calculate. You can obtain two different powers. You can obtain two different powers. Okay, so what are they? Real power and reactance power. Real power and reactance power. Generally, the real power is the actual power that will be attained. Reactance power, it's an imaginary power. Okay, so to represent this, we have considered a triangle like this, where this is your x-axis, which shows, this is your x-axis. This is your x-axis, where this gives you the real power. So for resistance is a component which gives or which dissipates heat. Okay, so this is your real power, and this imaginary axis indicates the reactive powers. Okay, so this is for inductance and this is for capacitance. So therefore you can represent this in terms of a simplified diagram, triangle. Okay, and this triangle is said to be called as power triangle, where the x-axis gives the real power, y-axis gives the reactive power. Here we have taken the resultant value of two reactances. So XL, XC, those resultant value has been considered and we have drawn like this. So the resultant value of these two powers will be called as apparent power, otherwise called as resultant power. Okay, so instantaneous power, real power, reactive power, apparent power. So four powers are there, out of which the real power is the actual power that will be inferred by the utilizers, right? So now when we talk about the power factors, what is this power factor? Is nothing but the cost value of angle between voltage and current. Cost value of the angle between voltage and current. So we got resistance, inductance, and capacitance. So for resistance, the voltage and current angle will be equal to 0. Therefore the power factor will be equal to 1. When we consider inductance, you'll be having the power factor value is equal to cos 90 degrees because the angle between voltage and current current is equal to 0, that angle between the voltage and current is equal to 90 degrees, therefore the cos 90 value is equal to 0, therefore the power factor is 0 power factor for inductance. Likewise for capacitance also it is 90 degrees again, therefore the power factor will be 0. Okay, but when we talk about practical cases, you don't have pure inductance and pure capacitance, therefore you will be having some resistance included, therefore the power factor will not be equal to 0, you will be getting a lagging power factor for inductance and leading power factor for capacitance. So that is what you have to consider. And of course from this power triangle, you can get another triangle called as impedance triangle, where the x-axis will be your resistance and y-axis, this part will be your reactance, and this will be your impedance. So when you replace this real power by resistance, reactive power by reactance, and of course apparent power by impedance, this triangle will become impedance triangle. So therefore this simple triangle indicates two different concepts. One is power triangle, other thing is impedance triangle. Okay, so that is what. Right. So now let us discuss some basic problems. So what is the average value? What is the average value? This is the first question that we have to discuss. Just a minute, I'll take this marker. Right. So we have to calculate the average power delivered to an impedance of 4 minus j3 ohms by a current of 5 cos 100t plus 100 amps. We have to calculate the average power delivered. So when we talk about the average power is nothing but called as real power. Average power is nothing but called as real power. So average power is nothing but called as real power. So which is nothing but average power. Okay, which is given by I square into R. So when we talk about this equation 5 cos 100t plus 100, okay, this can be related to, okay, Im into cos of omega t plus 5. Omega t plus 5. Okay, so omega is nothing but 100, phi is nothing but again 100. So Im is nothing but 5. Okay, when we talk about this 4 minus j, so this is R minus jx, therefore R is equal to 4. So here, what is this I? This I is nothing but IRMS value. So here when we compare this equation, phi is equal to Im, but IRMS is given by Im by root 2. So therefore replace this Im by phi here. So therefore you'll be getting 5 divided by root 2. Okay, so therefore using in this formula, this is equal to 5 divided by root 2 whole square into resistance value is 4. So therefore you will be getting 50 watts. 50. The unit of power is watts. So therefore the answer is 50 watts. So this is the answer. Okay, now the voltage applied to a circuit. Okay, voltage applied to the circuit is 100 root 2 cos 100 t, and of course the circuit draws a current of 100 root 2 sin 100 t plus pi by 4. Okay, so we have to taking the voltage as reference phasor, the phasor representation of the current in amperes. We have to give the phasor representation of current. So this is the current value. So replaces as 10 root 2. Okay, and of course the angle here, angle is plus pi by 4. Therefore make it as minus pi by 4. So this is your phasor representation of your angle, current. Next, when you talk about the RMS value of half-wave rectified symmetrical square wave current, so RMS value of half-wave rectified, okay, so the current value is 2 amperes. Therefore we can say RMS value, okay, it is given by Im divided by 2. Okay, so this is equal to 1 amp. Okay, so we have discussed in the previous formula that IRMS for half-wave rectified is Im by 2. Therefore, you will be getting 1 amp. Okay, now in the next subsequent classes, we will be discussing about something on RLC combination circuits. In the sense that it may be connected in series, it may be connected in parallel. So out of which you can obtain something called as resonance, and of course some more concepts. Right. So that's all for today's session. Good evening. Thank you.